Again, welcome back to the latest lecture session. Again, as is the norm, let's say, let's have a quick recap of what we have been up to, right? In the context of natural attenuation, right? We are trying to understand the system, let's say, and also predict some of the relevant constants and so on. So in that context, we were looking at a particular example, right? In that particular example, what did we have? I think we had a site contaminated with, I think, TCE, right? And then, we looked at different cases. As in one case, we tried to understand the system in terms of, let's say, laboratory experiments, which we refer to as the microcosm studies, right? As in, we took the sample from the aquifer, let's say, brought it to the lab, spiked it with different concentrations, let's say, of the TCE, and then measured the loss with time, right? Or change in concentration with time, and then try to fit the relevant model from our mass balance to that particular data, and then get the relevant rate constant and so on and so forth. And part B, let's look at what we have for part B. So again, as a quick recap, we have a site contaminated with TCE and fuel hydrocarbons, right? So this will be the electron donor fuel hydrocarbon, because it's the carbon here is what can I say, relatively more reduced, right, when compared to the carbon in TCE, let's say, right? And this is the compound that we are trying to look at. Obviously, we need both the electron donor and the electron acceptor here, right, for the redox process to go through. That's something to keep in mind. And for remedial option, we are looking at natural attenuation and microcosm studies. We looked at that. We'll again have a brief look at that to evaluate the first order observed rate constant for TCE loss. And then we also have the field data, the actual field data, right? Keep in mind this is the actual field data now. For the first, and we are asked to calculate the first order rate constant from that field data too. But obviously, we are asked to look at lab data as part A, and then for part B, we considered the field data with assumption of only plug flow. As in, when we talk about plug flow, what is it that we are referring to? That we are considering obviously, microbial activity and thus degradation, and any adsorption or desorption from the groundwater into the soil, or desorption from the soil into the groundwater. That's one aspect. But obviously, when we say plug flow, we are also assuming that, or not assuming, pardon me, we are also going to look at the effects of advection, let's say, right. So that's something we considered, or we are going to consider, pardon me. And then finally, though, field data with the assumption of Advection-Dispersion model, right. So in the case that in the what we say plug flow model, we haven't considered dispersion and diffusion, right. But in part C, let's say, we are going to look at obviously the most realistic scenario out there, which is the one with microbial activity, adsorption and desorption from or into the soil, right, and then advection, as in groundwater transporting the contaminant, along with its flow, let's say, right. That's one case, which is advection, and then dispersion now, right. So that's the case for part C now. Let's have a quick recap of what we have been up to for part A. So part A, microcosm studies, right. I just have the soil and groundwater here, contaminated groundwater and contaminated soil, obviously. And I think we have the relevant data somewhere here, right. We have the data here for total TCE concentration and time in days, yes. So I have this particular set of information here. And how did we go about that? More or less, we know that for mass balance, it's from mass balance, it's dC by dt equal to rate of formation minus rate of loss, right. And while either applying it to the entire system, as in both the soil or the groundwater, or applying it to, let's say, just the groundwater, we can come up with different ways. And I think we came up with something like Ct by C naught is equal to e to the power of minus k star t, right. So obviously, as you can see, we can even replace Ct by C total here, or this C T is the concentration in groundwater, right, but we have the total TCE concentration, right. So we have C total, let's say, at time t, that's the total concentration. Yes, there is a considerable difference here, but as you see, if you look at the model, right, though, let's say, and even the way that we derived that, let's say, we can even stick with the total concentration too, and that's why I believe we fitted this model, and we calculate a particular value of k star, the observed rate constant, right, and k star, it's affected by the retardation factor, right. So that's something we looked at in the mass balance in some detail. So now we are going to move on to part B, let's say, right, and what are we going to, or how are we going to go about it? First, let's look at the data. So what do I have? I have distance, right, and then the concentration. This is from the field obviously, and along the center line of the contaminated plume. So, if this is the top view, let us say, and let us say this is the center line of the plume, assuming that. So, I have 0, 10, 20, so on and so forth until 80 meters, and we have the relevant what do we say, readings at that particular case or at those particular sampling sites, and we see that obviously as expected concentration decreases, yes. And here obviously we are assuming that this system is at steady state or has reached steady state, right. If it hasn't though, then we obviously need more data at the same particular location. Let us say when the distance is at 10 meters from your reference, you will need what we say, data with different times and so on, if the system is not at steady state, right. Even then we can plug it into a relevant differential equation, let us say, not differential equation, the solution to our differential equation, and get it done, right. So, again this is the data that we have, but I think we came up or used the mass balance, right, or applied the mass balance, pardon me, for the context of advection, in the context of advection and adsorption and desorption, right, adsorption and desorption, obviously microbial activity, right. And in that context I think we came up with something like dC by d tau, right, is equal to minus k star tau, I believe, if I am not wrong, or I think we ended up with C by C naught is equal to e to the power of minus k star tau, right, k star, again the observed rate constant, let us say, and that is equal to k by r, and I think tau obviously is a function of x, right, obviously because dC by d tau, right, as we know here, as you can see, concentration changes with distance. So, we got the the initial equation was dC by dx, or the concentration was changing with distance or is changing with distance. In a plug flow reactor, obviously that is what you would observe, right. And obviously when we plugged in the relevant what do we say, aspects, though when we try to simplify it, we had a different term, and what was that? I think we have tau here, and how was that equal to, how is that related to x? I think we had it by the seepage velocity, u by epsilon, and r here, right. I think this is what we had with respect to tau here, right, and that is what you see here, right. So, now we are going to fit this model, right, they are going to fit this model to this data, all this data, and then calculate the rate constant, right. So, let us look at that for now. So, here I have the relevant data and the relevant constants written down, so that we can go ahead without a greater delay, let us say. So, here I have the data for distance, right, and here I have the concentration, that is the observed concentration from the field data, right, and here obviously I have wrote it down as theta because I could not find tau here, but obviously this is tau equal to x times r, or the retardation factor, by the seepage velocity, right. The seepage velocity is nothing but Darcy's velocity, as you can see here. This is the Darcy's velocity here, right, Ki, yes. How do you get the Darcy's velocity? It was not given in the relevant question, but you had the hydraulic conductivity and the gradient, let us say, right, energy gradient or such, and you know that this Darcy's velocity is equal to Ki, right, and that is what we see out here, right. And here we have the porosity, and from that I am able to calculate the relevant seepage velocity. Again to refresh your memory, what is the seepage velocity and how is this different from Darcy's velocity? So, for example, let us say if the groundwater is flowing towards you, let us say from my direction, let us say, right. So, for obviously you are going to have soil and then the pore space occupied by the groundwater, yes. So, obviously the groundwater has a limited or only a fraction of the area available to it, it does not have the entire area, right. But the Darcy's velocity, let us say for layman's terms, you can understand that it is more or less considered the normalized area, let us say, right. So, in that context, obviously though, what is the seepage velocity? Seepage velocity is the actual velocity of this groundwater through the pores. Obviously now the seepage velocity is going to be greater than the the Darcy's velocity, right. So, in that context, obviously I need to look at the relevant difference in cross sectional areas and such, and for that obviously by dividing Darcy's velocity by porosity, I can get my seepage velocity, right. So, that is what we have here, and we were somewhere else out here. So, theta, calculating theta, right, x is this distance, r retardation factor, I think we can calculate that, right. 1 plus rho b into Kp by porosity. Based on that, we can calculate this R to be retardation factor to be 10.45. And now let us move on and calculate Ct though, right, Ct or C tau, pardon me, or C at x. I should not have written this as Ct, but I could not find the symbol tau though, right. Anyway, this is C tau, maybe I will write that as tau, right. Okay, so I think that is better, C at tau or C at any distance x now, right. Again, what is the approach here? We have what do we say, concentrations at a given or at certain distances along the center line of the plume. That is the observed data. So, for some assumed rate constant, let us say, and depending upon your level of confidence in the C naught, you know, some assumed value of C naught 2, you can end up with, you know, different models, let us say, that predict this particular concentration at different distances, right, or distance along the center line, yes. But obviously, your particular predicted data, let us say your model data should obviously be what do we say, relatively similar to the relevant field data, right. So, obviously, how do we go about, you know, getting this particular job done? By minimizing the error, but obviously error you will have positive and negative error. So, we look at the square of the error. So, obviously, you have many data points. So, we look at the sum of the squared errors, right, and then we try to minimize the sum of squared errors. And one other aspect that is obviously taken into account when you square the error is that we also give considerable importance or greater weightage to the outliers, let us say, right. Again, that is something to keep in mind. So, again, sum of squared errors, and then we ask solver or let us say any other, you know, what do we say, mathematical tool can be used, but in Excel we have this particular tool called solver, right, and we use that to minimize this sum of squared errors, right. And when we minimize that sum of squared error, what does that mean? That more or less, you know, tells us that that particular value of rate constant, which gives you the minimum sum of squared errors, is the best fit, right, for that particular data, right. Okay, so let us go on and look at that. Obviously, to calculate the error, I need to calculate the C modeled value, right. I am calculating that. So, C modeled value is equal to C naught, which is here, right. H2 is, you know, 982, and then it is C naught into e to the power of minus k tau, right. So, I think that is what I have here. Where do I have the k here? Okay, that is k here. This is the initial value, or I guess this is the answer because I already looked at that. So, one minor change I made compared to how I worked it out last time was that last time I believe I worked it out in terms of I mean the rate constant for in the terms of units of per second or per day though. But what I should have conveyed at that stage was that, let us say, you know, obviously the rate constant in this natural attenuation, let us say, is going to be relatively less, right. So, if I look at units of per day or per second, let us say, any minor change, let us say, in the particular value of the k, when I write down the units as per second, let us say, will have a great what do we say, difference when I write down the unit in terms of per year, let us say, right. So, in such cases, let us say, you know, when I look at per second, let us say, and that can have a greater effect on my relevant results, let us say, because even a minor change can, you know, change the system considerably. Excel will sometimes have a difficulty in converging to the solution. So, in general, right, you know, try to avoid such situations, and to avoid that I am, you know, having the units of rate constant here in terms of per year. That is why obviously I have 365 days per year, 24 hours per day, and 3600 I think seconds for the relevant hour and such, right. So, that is why I normalize that here. So, I have C naught, Ct or C tau equal to C naught, which is here 982 into e to the power of minus k, this is my trial value, let us say, right, into tau, and this is the tau here. Tau obviously is dependent upon x, r, and the seepage velocity, right. That is what I have here, and we set that up. For now, let us choose some other value, let us say, you know, let us choose some trial, maybe I will go with 10, okay. So, 10 is my relevant k star, let us say, okay, 10 per year now, right. So, keep in mind it is 10 per year, and let us go ahead and calculate that. So, I have this particular value, right, distance times I believe retardation factor by the seepage velocity, that is what we have here, right. And let me just drag drop that here, okay. So, now I have the tau at different particular distances, right, and now same case I will calculate the C tau at different tau. So, again this is tau, right. Okay, I did not get that right. So, now I have C tau here, right, and as you see, I think if I already plotted that here. So, series 1, let us look at this data. So, the blue data set is the actual data here, right, and this orange colored data or the data set that is colored orange, let us say, is the model data. As you see, right, you can clearly see, at least for the rate constant that we start out with, let us say, which is what we say 10 per year, you see that the relevant what we say model is not doing a good job in approximating the relevant variable here, right. But how is that, or how do I go about that? Obviously by trial and error, such that the sum of squared errors is minimum here. For example, obviously here, as you can see, there is considerable error here for at each more or less each data point here, right. So, obviously we try to minimize that, and so here we calculate that error. As you can see, C modeled, this is C modeled minus C observed, that is the error here, and here I am going to take the square of that error, right, that is what I have here, right, and here I have sum of the squares of these errors, right. And now I am going to go to solver, and I go to data analysis, right, solver, pardon me, and I set the target cell. Which cell am I trying to change, right? I am trying to change, or this target cell obviously needs to be the one that I am trying to minimize here, right. So, that is going to be my sum of squared errors relevant cell, right. So, that is going to be, okay, it looks like F9 was already selected. So, it is F9, and what do I want that to be? Do I want the sum of squared errors to be the maximum? No, I want it to be the minimum. And how can I get to that particular minimum value? By changing this particular cell, right, which is the rate constant here, right. So, if you want to, you can also consider that the initial concentration of 982 milligram per liter is also, let us say, an unknown, right, because not because, let us say, but you typically have greater confidence in the initial sample that you collected. But if you think you have less confidence, obviously you can set that to be a variable too, right. Again, so sum of squared errors, I want that to be minimized by changing this value of k. Obviously, because I tied in this calculation of cell to k here, right, because we use k here in calculating C model, obviously that is going to affect the sum of squared errors, right. So, let us ask for it to solve for it, and okay, I am going to ask for it to keep the solver solution, and now you see that I end up with, what do we say, the relatively accurate estimate of the k star, which is 2.9 per year. And now obviously you see that both the observed and the observed and the model values, let us say, are in close consonance with each other, right, or the error is relatively less, or the minimum that it can be, right. Again, as you can see now, the error is considerably less now when compared to what it was earlier, let us say, right. Again, this is the obvious approach to go about getting things done in this context, right. So, keep in mind that we are conducting regression, and this is something you should, or most people out there should be familiar with, right. Again, obviously the more the data, the greater the confidence that I will have in my particular regression, obviously, right, so that I can capture the trend. So, in this regression, let us say, again, layman's terms, obviously what are we trying to do? We are trying to capture the trend, right, we are trying to capture the trend here, right. So, if I have, let us say, only 2 data points, there are many models or many trends that can be attributed such that they satisfy the conditions for those 2 data points. But the greater the number of data, let us say, right, obviously the model itself, I can understand that either from material balance or from looking at the data, right. But obviously let us say any deviations or such will be more accurately captured, obviously let us say, if I have the greater data sets, right. Again, keep that in mind. So, obviously let me just try out something here with one, let us say, value that is less than it, and let us hit enter, and obviously now you see that it what do we say, the concentrations are again different from that of the observed values, right. So, earlier we looked at the case of 10 and I just plugged in for case of 1, and again you see that it is moving away from the observed data, right. So, if I go to 2, right, as we know the true value is 2.97. So, now again it is approaching the true data, and now let us say if I end up with plug in the true value, which was 2.97 if I am not wrong, right. You see that you more or less end up with the end up closely approximating your particular observed data, right. So, I guess with that we will wrap up part B, and now we will move on to part C, right. So, what is here in part C now? So, part C we are asked to look at advection and dispersion model, right. So, dispersion obviously again I think we looked at that, let us say because of the tortuous path that a particular water molecule and thus the contaminant let us say can take in subsurface, as in you have soil particles let us say, right, closely what do we say, in close proximity, right, or in proximity, and thus obviously the water molecule from particular location can take different paths from the same location let us say, right, starting from the same initial point let us say, right. So, obviously you are going to have what do we say, decrease in concentration, and again you are going to also have molecular diffusion let us say, right. And thus let us say dispersion, let us say in this context we are looking at both these aspects, and obviously here let us look at how we are looking at the dispersion coefficient. So, obviously we need to calculate dispersion coefficient. Here we are going to consider that to be dispersivity times actual groundwater velocity plus diffusion coefficient, right. So, here we are looking at both diffusion and dispersion when we talk to or refer to as dispersion coefficient, right. Again, what was the mass balance, or what is the fundamental mass balance? So, it is dC by dt, and assuming that is there is flow in only one direction. So, C will change in only along x direction is equal to the diffusion coefficient times derivative of or second derivative of C with respect to x plus or minus any sources or sinks or any rate of formation minus rate of loss. This is the fundamental mass balance equation. So, if it is at steady state, obviously this will end up being 0, and in part B we assume that this was 0, but now we can't. So, here instead of diffusion coefficient I am now going to have dispersion coefficient, right, and again rate of formation or rate of loss for that particular compound. In our case the compound is being lost due to microbial activity, right. So, in that context obviously I can plug that in and so on and so forth and solve for this, but obviously this is a second order differential equation. So, we did look at a particular model that was developed I think at and it is available in Metcalfe and Eddy, right. So, C as a function of Peclet number, right, and what is this and also a constant A, right, a constant A and a Peclet number here. So, A obviously depends upon, as you can see, K, tau and the Peclet number, right, or in terms of K and the diffusion coefficient and I believe the seepage velocity. So, again interchangeable terms here obviously, right, and but obviously if they are interchangeable you are going to have a relationship between Peclet number and what is this particular numerator and what is this in the denominator. So, if you look at that particular Peclet number, it gives you an idea about, if you look at that particular system, the transport, let us say the relative transport or importance of transport, if I can say that again in layman's terms, of the contaminant by advection in the numerator and by dispersion let us say in the denominator, right. So, here we have the terms for advection based transport and here for the dispersion based let us say, again a generic layman's term anyway, right. So, again Peclet number and so on and so forth, this obviously is the seepage velocity, right, Q is the groundwater flow, A is the cross sectional area divided by porosity, because then this will be the area available for the groundwater to flow through, right, or the cross sectional area of the relevant pores, if you can think of that, and I can now get the seepage velocity tau, right, that is something I looked at, but slightly different in this context here though, right. Again I can go ahead and solve for this, right, I can fit this model and solve. So, let us look at that particular case. Again, which data am I going to fit it to? I am going to fit it to the field data again, the same field data for that I used in part B, right, but now I am going to use that for part C now, right. So, let us look at that. I already have that here somewhere, right. So, I have that here. So, I have distance again and now Peclet number, we are calculating that out here, and aqueous concentration, this is the observed data, model concentration based on some particular values of C naught and A, let us say the constant. So, instead of Peclet number I have it in terms of A and C naught let us say, right, and here, right, we can calculate that, and obviously A is dependent upon K, as you can see, right, Again, A is dependent upon K and the groundwater velocity, or I think the seepage velocity too, and the dispersion coefficient and so on and so forth. So I plug these in. Again, same approach as last time. What was that? I mean, we looked at minimizing the sum of squared errors by changing some of these cells. So I can either ask for Excel to change this constant, not constant, variable A, which is again dependent upon the rate constant, or ask the Excel to change this particular rate constant directly, and I end up with a particular model, and I can get the relevant rate constant from there. Again, here I have it in meter per second. I should have had it in per year anyway, right? So again, that's the hydraulic conductivity, pardon me, in per days here. This is the value that I ended up with, right? Again, as you can see, there is a considerably, what do we say, there is a good fit out here for after I solve for the relevant solution, right? So let me just try one thing out here. Let's say I want to say this is in per days, right? So let me get the key here, and I'm looking for equal to here. Cut, please.
Yes, sir.
Just equal to. Okay, go ahead.
Ready, sir?
Yeah.
3, 2, 1, start.
So rather than having it in per day, let's try to understand it in terms of per year, right? So that's going to be this into 365 and enter. So it turns out to be around 14.6 per year, right? Earlier we had around, I think, 3 or so per year, right? Again, keep in mind that there might have been minor errors. Let's say if even one of these variables wasn't plugged in right, or if I rounded out some of the variables, but it should be in this particular ballpark, and that is expected, right? So like with that, I'll move on to, or go back to the relevant question again, right? So this is a typical scenario that you would see or expect in the field though, right? Part A, how is that easier, or not part A, the microcosm studies, why are they better or easier for you? Obviously because controlled environment, let's say, right, and I can get that done, yes. And let's say resources and such might be easier too, yes. But obviously if I want to approximate the field conditions better, obviously I need to get the data from the field, and in that case part B is better. And obviously C is the particular case that most closely reflects the real life scenario, let's say, or the practical scenario. But obviously for this, as you see, you need more and more resources, and more, what do we say, it's more and more data intensive, let's say getting the dispersion coefficient or such, that's tricky because it's not going to be typically uniform and such. So there are aspects involved. So it's a balance between the resources and the kind of information that you are looking for, right? So I guess with that I'm almost up with time, and by now though we are more or less done with rather all the aspects with respect to natural attenuation, right? And natural attenuation is the last topic, or the last aspect we are going to discuss in terms of remediation of contaminated groundwater. So we will look at one what do we say, case study, let's say, in the next session that's relevant to natural attenuation, and then we will move on to the relevant aspects of dealing with the other set of contamination, let's say, or other aspect within contamination. What is that? Obviously until now, what have we looked at? We have looked at remediating contaminated groundwater. Obviously in the subsurface you are also going to have soil, let's say. So we are going to look at those cases, let's say, when only the soil is contaminated, or both the soil and the groundwater are contaminated, right? So with that, I'll end today's session, and thank you.